You've seen them, right? Those absolutely massive cylindrical steel tanks on the side of the highway. Ever stop and think, what in the world is holding all that together? Well, today we're going to peek behind the curtain and get into API 650. It's basically the secret rulebook for these giant structures that are honestly a huge part of our world, even if we never see the engineering that goes into them.
I mean, just look at the scale of this thing. It's kind of mind-boggling. We're talking millions of gallons, immense pressure. Getting the design on something like this wrong? That's just not an option. The stakes are ridiculously high, and that's exactly why you need a super detailed, globally recognized standard to make sure it's done right.
So what is this API 650 thing really? Well, it's not just some dusty document sitting on a shelf. The best way to think about it is as a playbook. It's all the collective wisdom of engineers, a super detailed blueprint for safety. It's what builders all over the world trust to make sure these tanks are tough enough to handle, well, everything.
All right, so here's the game plan for this explainer. We're basically going to build one of these tanks from the ground up, following the rules. We'll start with the safety blueprint, then move on to the foundation, design the shell, and finally, we'll get into the math that holds it all together.
Okay, first up, the blueprint for safety. And this is key because one of these tanks is way more than just a big metal can. Every single choice, every little detail in the design is a deliberate move to prevent things from going wrong.
And here's a perfect example of that mindset, something called corrosion allowance. See, engineers know for a fact that over the years, decades really, rust is going to happen. It's going to slowly eat away at the steel. So what do? They add extra thickness right from the very beginning. It's exactly like putting extra tread on a tire. You're planning for the wear and tear long before it ever starts.
All right, we've got the safety philosophy down. Now it's time to actually start building. And of course, we're starting from the ground up with the foundation. Everything, and I mean everything, depends on getting this part right.
And check out this number because it really shows you how precise this gets. 6 millimeters. The standard says that even after you account for decades of corrosion, the steel on the floor of the tank can never be thinner than this. That is a hard and fast, non-negotiable rule for making sure the whole thing stays solid.
Now here's one of those little details that makes a huge difference. This thing is called a drip ring, and its job is super simple but absolutely vital. It's designed to keep rainwater from getting underneath the tank, where it could cause all sorts of corrosion problems. It's just a tiny little feature, but it protects the entire foundation. Pretty clever, right?
Okay, so right at the edge of the tank's floor, you have what are called annular plates. You can think of this as a critical connection point. It's basically a ring of thicker, beefier steel plates, and it has to take all the massive weight from the vertical walls and transfer it safely to the foundation.
And, you know, the thickness of these plates isn't just some random number they pull out of a hat. It's all connected. The more stress that's coming down from that very first bottom layer of the tank wall, the thicker that annular plate has to be. It's a direct relationship.
This table from the standard lays it out perfectly. You can see, right, if the stress on that first shell course is, say, 190 megapascals, then a 6 millimeter plate is fine. But look what happens when that stress jumps up to 250. Bam! The standard says you need a much thicker 9 millimeter plate. It's a perfect example of how the force dictates the design.
All right, our foundation is solid. Time to go vertical. Now we're talking about the shell, the walls that literally have to hold everything in. This is where the real pressure is.
So the shell isn't just one giant piece of steel. It's actually built in these horizontal layers, or courses. Now think about it like you're diving in a pool. The deeper you go, the more pressure you feel, right? It's the exact same principle here. The pressure is greatest at the bottom, so the thickest, strongest steel plates are always at the base, and they get thinner as you go up the tank.
This brings up a super important question, right? How much stress can you actually put on the steel before you're in trouble? Well, engineers have a term for this: allowable stress. And the key thing to remember is this is not the breaking point of the steel. Not even close. It's a much lower number that builds in a massive safety cushion.
Okay, let's take a look at a really common type of steel, A36. The tables in the actual standard are massive, but this one little row tells you everything you need to know. The steel itself has a yield strength of 250 megapascals, but when an engineer is designing the tank, the standard only lets them use 160. That gap between 250 and 160, that's your safety factor, baked right into the rules.
And that term, minimum yield strength, it's super important. The paperclip analogy is honestly the best way to get it. You know how you can bend the paperclip a little bit and it just springs right back? But if you bend it too far, It's permanently bent. It won't go back. That exact point where it goes from springing back to staying bent, that's the yield strength.
Okay, so we've got our safety principles, we've got our foundation, we know about our materials. Now for the last piece of the puzzle, the math. This is how engineers take all these rules and turn them into an actual physical design.
Which brings us to the big question, the one that every engineer has to answer. After all of that, how thick does the steel actually need to be?
And the answer is in this formula. Now, hey, don't panic. We're not going to make you do any calculus here. But I want you to see it because this isn't just a bunch of letters and numbers. This is the recipe for safety. This is what turns all those principles into one crucial number: how thick the steel needs to be.
And when you break it down, it's actually pretty straightforward. You start with D for the tank's diameter, and H for the height of the liquid inside, because bigger and taller means more pressure. Then you divide all that by SD, which is that safe, allowable stress for the steel we picked. And then at the very end, you add CA, our old friend the corrosion allowance, to make sure it lasts for decades. See? It all connects.
Now, before any of these tanks can actually be used, they have to pass a final exam. It's a one-time stress test where they fill the entire thing with water. And for this one test, and only this test, the standard lets engineers use a slightly higher stress limit, STRET. It's a way to really push the tank and prove without a doubt that the design and the construction work are solid.
And in the end, that's what it's all about. It's not just a random collection of rules. Every single plate, every weld, every single calculation, they all work together to create one single, incredibly robust structure. And it's all designed for just one purpose: keeping what's inside, safely.
So what are the big takeaways here? Well, first, it's that standards like API650 are how we turn cool engineering ideas into things that are actually safe in the real world. Second, every single number, every dimension, is there for a reason. It's a calculated defense against pressure and corrosion. And third, you have to remember that this is all one big system. Every part affects every other part.
You know, standards like this are amazing, really. They're built on decades of real-world experience, on lessons that were often learned the hard way. But it kind of leaves you with a big question, doesn't it? If everything we do today is based on what we learned in the past, what's next? What new materials or new technologies will push the next big leap forward in safety?